Okay, so good afternoon, everybody. I'm getting some feedback here. Welcome to the people who are sitting online. We have quite a number of online presenters, so we'll see how that goes. And our first online presenter is Fengxuan Li. If she can just maybe share from her screen, we don't have her presentation. If you'd like to share your screen, and then you can continue with your presentation. It's about indoor environmental factors affecting the productivity of workers engaged in research in office buildings. So that's all of us. Fengxuan, if you'd like to indicate that you are here and maybe switch on your camera and your microphone so we can say hello to you.
Hi, everyone.
Thank you. Are you going to have a presentation screen that you want to share, or are you guys just going to speak?
Okay, I'm going to share my screen.
Okay, great, thank you. And then the moment your screen is live, you can start.
Okay.
And I'll start the clock. You've got 10 minutes.
Okay, thank you. Sorry, wait a minute. I got to open my.
Okay, thank you. We can see you.
Okay. Okay. Thank you, everyone, for attending my presentation. And it's about the indoor environmental factors affecting the productivity of workers in office buildings. My presentation is based on these 4 contents, including background, literature review, methodology, and the results and discussion. First, for the background, it's indoor environmental quality has played an essential role in human health, well-being, and productivity, especially in recent years. Well-being and mental health has been an illegal requirement in many building standards, such as well building standards. And second, workplace productivity has been a growing concern following the recognition of the potential business benefits from a healthy and happy workforce. Such as previous research has estimated that the cost from human productivity loss has accounted for 20% of the organization cost in total. And the last is that there are only few about the focusing on the territory buildings where the office users engaged in academic research, as academic research work may be slightly different than any other type of works because they require a prolonged concentration and creativity. So they might have different preferences on the working environment than people doing other types of work. Based on these concerns, we designed a questionnaire that's aiming for people who engaged in academic work to explore what they prefer to have in working environment. And so by doing that, we first want to do a pilot study to validate the indoor environmental factors affecting their productivity. Then for the indoor environmental factors, we do a preliminary literature review to including thermal comfort, indoor air quality, lighting, noise, and the office layouts. These are the 5 basic aspects that we think people care about, and they think they have their satisfaction with these aspects may affecting their productivity. And the table 1 gives information about our drafted questionnaire. The first part is about the participants' basic information, including age group, gender, and their ethnicity, office buildings, and office types. And for the indoor elements, we divide in total there are 15. So these 15 elements are the important ones in our questionnaire survey, and our questions are mainly focusing on these 15 aspects. So the students will give whether they think they got some impacts from these elements, see whether they think these elements are logical, or if they think we should include it in the office indoor environment. And based on their reply, we later will refine our questionnaire. And for the methodology, first of all, the literacy review part, the search terms are productivity, performance, office, workplace. We use this because these are the most cited one in previous articles. And the database are Web of Science because it's the largest and including many huge authors. And the only articles that are published in the first quintile and the second quintile journals are included in our review because we think these are are very representative for the quality of the papers. And then based on the factors from the review, as we said before, we developed the questionnaire survey, and then we distribute it to 12 postgraduate students in engineering buildings in 405, now 1, and now 6 in the University of Auckland. Because we mainly do this based on the concern of the data accessibility. It's easier for us to get the data back. And table 2 gives a demographic characters of the respondents. I'd say most of our respondents are around their 20 to 39 age group, because this is expected because the students, the respondents are mostly students. And most of the PhD students are working in shared rooms, shared with more than 10 people. This is also consistent with our office layout distribution in the university. And then for Figure 1 gives the general distribution of the Likert score of the 15 indoor elements based on the mean value of each indoor factor. We can see that the noise level, temperature, air quality, lighting, soundproofing, cleanliness, workstation setup, and visual privacy are the important factors that are affecting people's productivity. The rest of the factors are also concerned as important ones, but compared to the formal 4 factors, they have less importance. And apart from that, we do comparative analysis based on age group and gender and office layout to see if there are any differences around each indoor element. We can see that for the age group, there are obvious differences among the factors around air quality, lighting, soundproofing, meeting rooms, and interior decoration, and storage place, and the number of lifts. Sorry. And the figure 3 shows the gender differences. We can see that each group is for the formal each indoor elements. The age group differences is similar to the gender ones. The temperature, air quality, and the light, the soundproofing, they show different, slightly differences. And then for the office layout, for workstation setup, visual privacy, meeting room, and the natural view, these four are the frequent ones that the people in different room types, they have different views. And that's the basic results. Based on the conclusion, we see that the noise, temperature, air quality, soundproofing, cleanliness, and lighting was the most reported factors affecting work productivity. And most of the factors included in the questionnaire are clear and explicit, except factors such as number of lifts and the availability of meeting and common rooms, because some students reported that they think these three factors are outside the office. They don't care this once they sit down on their desk to work on their tasks. And then office users have different preferences on the indoor factors across the age groups, gender, and office buildings. Yeah, that's all. Thank you. Do you have any questions?
Thank you very much. Give her a hand.
Thank you.
Is there any questions? I think we can have one question. We try and make up a little bit of time. Is there anybody who has a question? Yes?
In relation to the gender and the age question and the difference in perceptions, I'm just quite interested. Did you look at the factors, or was that just a question that you had, or was there a reason why you wanted to look at the differences from a gender and an age perspective? And if so, what were the factors that caused the differences between?
Yeah, I want to look at why there are differences between the age group and gender group. What causes the differences?
And are you going to look at another population group that's not just engineers?
No, currently the focus group are only for engineer students.
Okay, thank you very much. Another question here? Aha. So thank you for the presentation. In terms of the sample group, do they have any prior knowledge of indoor environmental quality design? And if so, do you think that would have affected their response?
Sorry, I would say that the sample group.
Did they have any prior knowledge?
Yeah, I think it will have some effects on their respondents. So to solve that problem, we included some introduction on the indoor environmental factors to the respondents. And then also based on the pilot study, we try to delete some factors that they think may be hard for them to understand in the real life, and add some terms that they think might be more understandable for them. Yeah.
Okay. Thanks. Thank you very much for that. Can we bring up the next presentation, and then Mohamadali, Morshedi, if you can maybe put your face up on the screen and switch on your microphone, and then we can all see you.
Yeah, sure.
Thank you.
Hello? Can you see my screen?
We can see your screen, yes, thank you. So you're going to talk about explaining the changes in the greenhouse gas emissions of New York City buildings. So over to you, thanks.
Yeah, thank you so much. Well, hello. Although it is almost 2 a.m. here in the US, I wanted to say good afternoon to everyone. And thank you for attending this session and listening to me. This is Mohamadali Morshedi, a PhD student at Purdue University. And it is my pleasure to present the findings of the research I conducted with my dearest friend, Arkaprabha Bhattacharyya, and also a PhD student at Purdue. And my great advisor, Professor Hastak, Professor of Civil Engineering and Construction Engineering Management at Purdue. So our research is on explaining the changes in the greenhouse gas emissions of New York City buildings. So in the presentation, I will start with our motivation to do this research, discuss our method, provide a very brief overview of the data set that we've used, and talk about the descriptive and predictive analysis results, and then conclude with our findings. So let me start with why this topic is important. As you can see in the left-hand side graph, 12% of the total US GHG emissions in 2018 was emitted from the buildings. And on the right-hand side, you can see that New York City is ranked third among the cities across the globe. Not in a good way, but in terms of GHG emissions. So controlling GHG emissions of NYC buildings not only is important to reduce the global GHG emissions, but also is important to draw conclusions and propose frameworks that can be applied to other cities and locations as well. So several studies have actually attempted to evaluate the impact of the policies aimed at reducing buildings' GHG emissions over time, but there are some gaps in the existing literature. First of all, most GHG emission prediction models use static snapshots of energy performance, and they tend to assign high weights to non-changeable features that are related to the floor area, for instance. And the last limitation is the prevalence of black box methods with limited insights for the policymakers. So our objectives are to identify NYC buildings with increasing and decreasing GHG emission patterns, and then we try to identify important changeable variables that have contributed most to the formation of these GHG emission patterns. So in this slide, you can see an overview of our method. We use the energy and water data disclosure for local law 84 data for 4 consecutive years from 2017 to 2020. And the data set is publicly available, and it includes large buildings over 25,000 square feet, and it has more than 25,000 data points with 67 attributes. So as you would imagine, we had to do a lot of pre-processing. During the pre-processing step, we reduced the number of independent variables, identified common buildings based on their unique IDs, remove outliers, and check for multi-collinearity issues. And then in the next step, we divided the buildings into 2 categories with increasing versus decreasing GHG emission trends. And the next step was developing a random forest prediction model and validating the results with 5-fold cross-validation. We then tried to optimize the model and conducted the variable importance analysis to identify the most influential factors in explaining the patterns. So let's start with model variables. GHG is our independent variable, which was normalized with respect to the floor area. The independent variables are the type and age of the building. The occupancy is is actually the percentage of the property that is occupied and operational. Energy star score is essentially the percentile ranking of the buildings among similar buildings across the US. And we have also gas and electricity consumption, which are weather normalized to take into account for the factors such as unusual, hotter, and colder than the normal climate for the building. So moving to the descriptive analysis result, as I mentioned before, we first categorize the buildings into two categories with increasing and decreasing GHG emission patterns. But what do we mean by that? To identify the GHG emission patterns, we use the emissions for all the 4 years of the data that we had. So the buildings that had a positive third order difference were labeled as the buildings with an increasing GHG pattern and vice versa. So a comparison of the buildings in the two categories show that most of the buildings are in the decreasing pattern, close to 66%, and which is consistent with the original data set that we used. Also, the buildings in the decreasing category are mostly residential, which may be an indicator of the relative effectiveness of the measures for controlling the GHG emission of residential as compared to commercial buildings in New York City. So but let's move to the predictive model development, which was through an iterative process. So as a first step, we selected the random forest model hyperparameters, such as the number of trees, the maximum depth of the tree, etc., and using a grid search approach. So which is basically exploring all the possible values for the hyperparameter. Next, this step was accompanied by model performance evaluation. So we use R-square and the mean absolute percentage error, and with 5-fold cross validation to evaluate the performance of the model. And then we did the feature importance analysis to determine the most important features. And in short, the variable importance analysis is about randomly permuting one of the predictors and observing the impact on the model performance. So the higher the impact, the more important is the variable in explaining the dependent variable. So based on the variable important analysis result, we removed the least important features and repeated the whole cycle again and again. So in this slide, you can see the variable importance analysis results. The plots show the amount of reduction in the R-square value when each of the predictors is removed for both categories of the buildings with decreasing pattern and increasing GHG emission patterns. So in the first cycle, we removed the buildings with the building type and occupancy level. And in the next cycle, age was removed from the predictors that could explain a decreasing GHG emission pattern. So in the end, the order of most important variables turned out to be different for the buildings with decreasing and increasing pattern. So as you can see, the order of the electricity consumption and gas consumption is different for the two categories. And we also have age for the increasing pattern as one of the important features and predictors. So okay, to make sense of the order of important variables for two categories, we compared the amount of reduction in the predictors from 2017 to 2020 for both categories. As you can see in this graph, the buildings with an increasing GHG emission pattern, they have experienced a 10% reduction in the energy star score, which shows that the buildings in this category have lost their energy efficiency as compared to other buildings across the US, maybe because of aging. And while on the other hand, the buildings with a decreasing pattern have maintained their ESS rank. And also, the buildings with a decreasing pattern category have also have been more successful in reducing the amount of energy and gas consumption levels as compared to the other category. So based on that, we can conclude that firstly, the buildings in the decreasing category are mostly residential, which may be an indicator of the relative effectiveness of the policies and measures that were undertaken from controlling the GHG emissions for residential buildings as compared to the commercial buildings. And secondly, the type of the building and the level of occupancy cannot explain GHG emission patterns. And the third conclusion is that the decrease in energy star score is associated with an increasing GHG emission pattern. And on the other hand, maintaining energy star score and accompanied with a significant reduction in electricity and gas consumption can explain the decrease, can explain the formation of a decreasing GHG emission pattern. So with that, I would like to open the floor for questions and comments, and thank everyone so much.
Thank you for that. Any questions? Come on. Some questions in the chat. Okay, this research occurred before the pandemic, and do you believe that data will change now as the use of buildings is changing due to home office, online learning, etc.?
Yes, that's a great question. So the occupancy is a variable that is related to the percentage of the building that is functional during the day. So the results show that the level of occupancy is not a predictor. I mean, if the building is functional, no matter how much the floor area is occupied, it is not going to affect the patterns. So, but if the building is shut off, that might be that's a different story, I guess. Did that answer the question?
I think so, yes. Thank you. Any other questions?
Sure.
So I want to know if you say that it makes sense that, of course, if you reduce the electricity and the gas consumption, that your greenhouse gas emissions will go down. But what was it that actually changed the gas consumption, for example? Is there a policy in New York that tried to step away from gas for heating and cooking and so on, or is it what caused that?
So yeah, that's a good question. I think that there are some policies with respect to changing the HVAC system. So that might have affected the electricity consumption, but for the gas consumption, I am not 100% sure to answer the question right now. But I can check that and get back to you later if possible.
Thank you. Thanks. And I think that is, unless there's another question in the room. No questions? Okay, thank you very much, and I hope you can have a good rest now that you know you've done your bit for the conference. Well done.
Yeah, sure. Thank you so much.
Thanks. Okay, so our next speaker is actually here in person, Zelinna Pablo, and she's going to talk about towards a theoretical understanding of BIM innovation success in facilities management, a comparison of actor network theory and diffusion of innovation theory.
Hello, everyone. My name is Zelinna Pablo. I'm a senior research fellow from Torrens University, Australia. I'm based in Sydney. My co-author is Dr. Ruwini from RMIT University. We're both very happy to be here. Next slide, please. The paper is part of a larger project, and our end goal for the big project was to develop a whole-of-life BIM maturity model that would provide a roadmap for successful BIM adoption for owner organizations. So we set out to develop a maturity model that would capture all stages of an asset's life cycle, including the often overlooked facilities management stage. So when we completed this project, we published the model in a journal article along with a practice guide, and you're going to see excerpts, I think, in the next slide, okay. But the paper that we're dealing with here describes the first stage of the project. When we said we wanted to develop a model that was empirically grounded and rooted in theory. So this paper describes our journey for theory selection. How do we select a theory with robust explanatory power for achieving BIM maturity, therefore translating it into successful adoption? Next slide, please. So today we're going to explore just two theories of innovation that have informed BIM adoption in the literature. There's diffusion of innovations theory, or DIT, and actor network theory, or ANT. We compare compare them because researchers in the past have said that they are two contrasting approaches to innovation. So theories tend to be hidden. Managers often don't talk about them, but they do have a potentially significant impact on practical matters, and we are going to demonstrate that here. We sort of unpack the theoretical assumptions of each theory, and we translate these into practical toolkits, and we show how they lead to very different pathways for BIM adoption success. And in the end, we conclude that both DIT and ANT have robust explanatory power. However, we do conclude that ANT is the stronger of the two for reasons that I'm going to explain later. Next slide. So before setting out to define our maturity model, we couldn't just go out and build one and populate it with random elements. We had to address a number of very basic questions. For example, when we talked about BIM, were we referring to technologies like hardware and software, or were we referring to something that was more social material? For example, were we just talking about the hardware, the software, the processes? And when you start talking about processes, they inevitably began to get linked to human factors. So researchers actually take different positions on this issue. Another question, do we see BIM as relatively stable, or do we see it as something that's always being created and recreated over its life? Again, researchers would say different things. So our answers to this question would very much shape the way that we would conceptualize BIM adoption and successful BIM adoption. So even the most practical managers, we argue, are likely to be driven by hidden theoretical assumptions. Next slide. The first theory we looked at was diffusion of innovations theory, and key concepts were shown on the slide. So DIT actually starts with the idea of an innovation, a new object or a new process. And in construction research, this tends to be discussed as the hardware or the software. Diffusion means that it's going to be adopted by groups. For example, the DIT calls them early adopters or laggards. The speed or the rate of adoption is shaped by a number of factors. Some are related to technology. The more complex, the less observable, the less trialable a technology is, then the harder it is to adopt. Others would be related to the social system. A second theory that we looked at was actor network theory, and again, key concepts were shown on the slide. So ANT researchers assume that all phenomena are networks of humans and non-humans that are tightly interlinked with one another, and the goal of every network is to sort of achieve convergence among these humans and these non-human actors. So actors agree to take on very tightly defined roles, often simplified roles. When these roles dovetail nicely, they click together, these are called adhesions in actor network theory. If they don't, and if there's role conflict or identity conflict, ANT researchers would refer to these as controversies. So as we built our conceptual foundations, we begin to see that the pathways of definitions of BIM success would begin to diverge. So if we stay, for example, on the DIT trajectory, we would assume that a new technology like BIM is separate from the social context. There would be hardware, there would be software, there would be the social context, they would have to be managed separately. We would have to assume that someone develops the innovation stabilizes, and once stable, the goal is to get more and more people to adopt it through communication, through information, through knowledge sharing. And again, this is called the process of adoption. If we took the ANT path, then we would see a completely different process. We would say that people and technologies are inextricably linked. You cannot manage one without managing the other. Changing the role of one would mean changing the role of everybody else in the network. And so the goal would always be to drive adhesions between the roles and to try to resolve gaps and controversies. So what does this mean for BIM adoption? Next slide, please. Under DIT, BIM adoption success basically means a critical mass of people would have to adopt BIM. Under ANT, BIM adoption success would be different. When humans and non-humans are together in a BIM network, then the goal would be to achieve adhesions and convergence and to resolve controversies. So in the next slide, we show that clarifying theoretical concepts and assumptions did allow us to build some very practical toolkits. So a manager driven by diffusion of innovations would ask a different set of questions. They would ask questions that are related, even without using the terms, they would ask questions related to homophily, trialability, complexity. Was there an opportunity to test or trial BIM? Did the champions communicate the benefits? If the answers were yes, then BIM adoption success would be more likely. An ANT toolkit would foreground different things. Who were the human actors? Who were the non-human actors? Did the roles dovetail or interdefine? And we can see that in the next slide. So again, a DIT toolkit would foreground some things, an ANT toolkit would foreground something else. So we built two toolkits from the theory. And we held them up as lenses to examine a case study. And we show some details in the next slide. They're quite small, but I'll just walk you through it. Our case study involved a US-based university, which was an early adopter. It's in the next, yes, that's it. It had a campus of 900 buildings. Construction projects were on an ongoing basis, and it had a dedicated facilities management unit. Data was gathered through a range of techniques. At the core were semi-structured interviews leading to about 200 pages of text. We analyzed data in 4 rounds of qualitative data analysis. And just to share some insights on the BIM adoption experience, use of BIM began when a professor doing research on BIM with graduate students eventually were embedded in construction projects in a dozen or so ongoing initiatives throughout the university. The overarching project director became interested and began formalizing BIM as a requirement through contracts, through recruitment criteria, and all was going well. And for a while, there was actually momentum in projects. But as these projects were completed and handover to facilities management began, it was found that facilities management people often struggled with incompatible files, incompatible systems, disjointed job descriptions. And to make things worse, key BIM champions eventually resigned. So at the time of this research, BIM was floundering a little bit. So next slide. Our data showed from early stages how many BIM drivers were actually linked to BIM success, but this was in the beginning. Code 1, for example, showed that BIM was being increasingly formalized for a time. Code 2 shows that it was formalized through selection criteria. And Code 3 shows the outcome. BIM adoption meant very tight coordination. Actors like designers were disciplined to better address clashes and conflicts. In contrast, in the next slide, data from facilities management showed significant hurdles, and for a while, BIM was largely abandoned. The champions left. Later, I'll show that there were issues with files and systems and job role compatibility. A recurring finding was that facilities management people felt no ownership about the models. They were not brought into the tent, so to speak, at early stages, and they felt that what they were getting were Hollywood-type BIM models, when in fact that wasn't what they needed, and what they felt they needed was actually just the data underpinning the models. So in the next slide, we're going to see that we held up the lenses of DIT and ANT to this case study, and both actually provided a good enough explanatory explanation of why BIM succeeded in the early stages and why it floundered a bit in the last stages. But still, after doing our analysis, we found, based on our categorization of data, that ANT had a little bit more explanatory power. Why was this? In the next slide, number 1, ANT provided a more parsimonious explanation. A small set of ANT concepts had the power to account for most of the story. So ANT concepts like adhesions, controversies, another term called obligatory points of passage, framed much of the causal explanations. We saw this over and over again in the data. In the next slide, for example, we will see that controversies were a recurring theme in many of the codes. Controversy in the form of file formats, controversies in the form of systems not matching, controversy in the form of job descriptions of humans not lining up with the requirements of setting up a new technology. And a second reason why we felt ANT was a bit stronger was because ANT appeared to deal with more fundamental root causes. DIT was surfacing symptoms. ANT seemed to account for the more fundamental or the more basic explanations that were underneath these symptoms. So it's a qualitative study. Much of it is in the paper. But in the end, what we decided to do was to take ANT forward, and we used ANT as a theoretical frame for developing our model. So the model has been published in Sustainability along with the practice guide, and you're going to see there that it's framed by ANT concepts. So thank you very much. And Ruwini and I are happy to take your questions.
Any questions from the floor, from the audience, from the chat? Okay, there we go. Great research, but I'm almost questioning whether the difficulties that companies face with BIM adoption are inherent to BIM, or if in fact they are related to the complexity of the design and construction process, and complexity that has now been evidenced through BIM. So what is your opinion on that?
Well, I guess it's partly both. In this case study that we investigated, it sort of started as a bottom-up approach. You know, in the States, they didn't have a mandatory policy back then, and also there wasn't. The case study was more like an innovation organization. So it's formulated as a casual bottom-up approach, and that's, I think, how it leads to these findings. But coming back to the question again, complexities are anyway around this policy process, people interaction. It's multidimensional, and also it's very dynamic and evolving, as Zelinna mentioned in her presentation. So, well, complexities are around until you reach to that maturity level. And I think that's why we need robust measurements and models to measure that maturity level until that organization has reached that maturity level.
Somebody typing in the moment. We'll see for that. While yes.
Thank you for your presentation. You just referred to the general BIM, but there is no discussion about the level of the adoption and the dimension of the BIM. And I just see in your some of your slides, the participants refer to the 3D model. There is a misunderstanding with the industry between the BIM and the 3D model. Majority of the industry, they just refer the 3D model to the BIM. So did you able to clarify those people, they just participate on the BIM, they're just really working on the BIM, what level of the BIM they adopted and what dimension of the BIM they adopted? Are they just go for the 40, 50, 60? Thank you very much.
Thank you for that question. I think it's need to be clarified here. What she mentioned in 3D in her presentation was a quotation we extracted from the person who was involved in this initiation of the BIM adoption process, where the first step was that he developed a 3D model back then, like in 2010. So that's what it is about that 3D term as such, but we have given a great detail of clarifications around different levels and level of details in our journal article in greater detail, and also there's a definition, number of definitions we adopted, and we provided a definition as well.
I see there's another question. How do you think does use an AND framework change the process of education using BIM models or the implementation of BIM processes? How does an AND framework change the process of education?
That's a great question too, I think, because in the case study organization, what they found out in the end was knowledge management was something they didn't take into account well in advance in the process, specifically because they had this bottom-up approach and casual sort of formulation of innovation in the organization. In the A&T framework, we definitely, I think in the model we included knowledge management as part of it in our final model that we published in the journal article. Adding on to that.
And adding to that, from an A&T researcher perspective, I think an education process would focus more not on individual human actors or on the BIM model itself. It would sort of focus on the relationship between the two. There would be an emphasis on why the two may or may not be dovetailing, and there would be an effort to address that. So again, the focus would be on things like resolving the controversies or achieving adhesions between the actors or between the files or between the systems. So it's always going to be an emphasis on what is taking place between elements of BIM.
Thank you very much. And I think we need to move on to our next speaker, Evelina Kaibach, who I think is also online, who's going to be talking about the digitalization of climate adaptation planning, the potential of simulation software tools for landscape design. That sounds quite interesting, Evelina. Have you loaded up? Okay, we can see the screen. You can proceed, thank you.
So I'm happy to present today my research on the digitalization of climate adaptation planning and analyzing the potential of simulation tools. My name is Zelinna. I'm a landscape architect specializing in climate adaptation planning, and this research is done in collaboration with my professor, Mohamadali. Firstly, climate change causes environmental, social and financial issues due to the high floods and heat waves. European Union is counting around 95 billion losses for the damaged facilities in 10 years, and it's predicted to grow. Therefore, the demand for effective climate adaptation concepts is growing. However, this is still dealing with low level of digitalization. This research seeks to investigate the capabilities and limitations of software tools suitable for the climate adaptation planning using the ISO 25010 standard. It also seeks to identify the needs and expectations of different project stakeholders regarding software tools, and the goal is to propose the roadmap how to select the most suitable tool for climate adaptation projects. So the questions covered in this research include the main advantages and disadvantages of each tool, also what are the needs of different stakeholders, and how to select a suitable tool. Currently, the literature review revealed that most of the papers are focusing on the functionality of a single software tool or specific climate adaptation measures such as green roofs, while other papers comparing different tools are not integrating ISO 25010 standard. And also the needs and the expectations of different project stakeholders are currently not researched, and there is rather no roadmap helping to select a suitable tool. So this research integrates inductive research method seeking to observe different patterns between software tools and without creating the predefined hypothesis. So the first phase of the research is focusing on the objective experiments with 5 different climate adaptation software tools implemented on a case study project, which represents a sustainable and climate adaptive neighborhood in the south of Germany. The evaluation of these tools are based on the ISO 25010 standard. And the second part of research interview different project stakeholders identifying different personas. So we see how this ISO 25010 framework was implemented into the research and which aspects were selected. And some aspects were added, such as compliance with sustainability certifications, such as LEED, BREEAM, DGNB, and information quality analysis. So these aspects are very relevant for the climate adaptation planning. And this research seeks to focus on the objective measures such as the incidence register, error register, training time, and so on. This research excludes subjective aspects such as software interface, recognizability, and so on. So the final findings show that the ISO framework helped to define the main aspects which are very important for the evaluation of climate adaptation software tools. And we see that green scenario and AST tool, which means adaptive support toolbox, collected the most of the points on functionality, as these tools are specifically designed for climate adaptation projects. But if we see the information quality, EnviMet has agreed advantages which can produce a very reliable and precise simulations on climate adaptation topics. But the software is rather complex, so it deals with the low performance efficiency. AST is relatively simple. It has a simple interface and it can be used intuitively and allows to compare different design decisions in a short time. However, it has no compatibility with other planning software tools and low relatability as it's an online-based tool. And the green scenario calculates the results in the interactive dashboard, which covers a number of aspects relevant for the climate adaptation projects. And this tool is based on the Rhino interface using a visual scripting method. It also requires specific tools, specific knowledge. Overall, a green scenario collected the most of the points on the software, comparing to other software tools, but as it's has a strong compatibility with other tools, as relatively a lot of functions covered in the software tool and quite high efficiency performance. The lowest points were collected by the CitySim tool, as it's defined as the least suitable for this task and for this case study. Next, the phase with the interviews. Firstly, 8 different personas were identified and chosen from different fields of knowledge like landscape, urban design, and water engineering, as well as clients from private and public companies. And the problems planners are often facing with the current software tools for the climate adaptation projects, that it's low interoperability, data accessibility, and monofunctional tools requiring specific licenses to use the software. Some of the planners mentioned that climate adaptation is a long explanatory process. Therefore, I think software tools would help to communicate with the clients while visualizing the climate adaptation planning effect on the climate. However, most of the clients are not convinced about the value of these tools, considering the time and costs needed. So further on, the interviews revealed that most of the planners are working with different information covering flood assessment, temperature, such as shading and sun hours, and they expect that software tools would be more efficient while using them. As they mentioned, often easy navigation is important for them, and interactive dashboards, but it's important that they get simultaneous feedback on the design process. Interestingly, that clients have different expectations towards visual output. That it highly depends on the persona, and some of them they expect to have visual information and some of them digital information supported with the sketches and storytelling methods. So finally, the proposal for the roadmap is follows. It requires the identification of climate adaptation objectives. From the objectives, key performance indicators should be also defined, helping to evaluate the effectiveness of the tools. Next, the expected output from the clients and the available resources for the project should be also identified and considered while selecting the software tools. Also, I would highly recommend to implement ISO 25010 framework, as it covers different important aspects for the software quality measures, and the prioritization of these tools is of these aspects is very important while selecting the tool before running the test phase. So after the test phase, it could be easily compared. So this research, excuse me, this research includes 5 different software tools which were implemented on this case study project, and each tool deals with some advantages and disadvantages. These were defined using 250-10 framework. Most of the tools deals with interoperability and data loss, and it requires relatively high time resources to produce precise and reliable simulations. However, the interviews revealed that simulations are rarely required from the clients, and it creates a barrier for the digitalization of climate adaptation planning. Further research could integrate more participants in the objective experiments, and also different climate adaptation projects could be tested with different software tools. And also to be very interesting to investigate how well sustainability requirements such as LEED, BREEAM, and DGNB are covered in each software tool. Thank you for your attention. I know it's a lot of information in a short time, but maybe you already have some questions.
Any questions from the floor on this? Why those particular 5 tools?
It was chosen the tools which were the most suitable for the climate adaptation projects, as there are not so many and they're included in the research. I think the number of tools are growing as I know that most of the planners are developing their own tools.
It's true. Any other questions? Okay, so thank you very much, Zelinna. That was very interesting. I think you've sort of put people's minds to spin at the moment. So we'll see, you might get some questions later on as they start really thinking about what you said and went back to read the paper. But I found it very interesting. Thank you very much for your presentation.
Thank you. So there was my contact. If you have questions, I'm happy to answer. Contact me by email or LinkedIn.
Okay, thank you very much. Okay, so our next presenter is in the room, Robert Crawford, who's going to talk about trends in residential sustainability measures in the state of Victoria.
Thank you. Excellent. Thanks, Stephen. Good afternoon, everyone, and also everyone online. I'm going to be talking about, as Christina said, trends in residential sustainability measures in the state of Victoria. This is based on some data that we obtained, a large database of building permit data for Victoria. It is just one output of a possible analysis that we could do with this data. There's also my colleague, Vidal Payton-Cole, second author on this paper, who is presenting another analysis of the data on Wednesday. And I'll go through and talk about a little bit about the database as we go through. And the 4 other colleagues on this paper are, they're part of a group called the Melbourne Data Analytics Platform, and they helped us with the cleaning and the analysis of the data as part of the University of Melbourne. Is there a pointer there? Did I see a, thank you. Great. Apologies for the green. The green and white doesn't really go well in this room, does it, on this screen? Yeah. So don't look at me, look at the side walls. So just to give you a little bit of context, the 26% of Australia's energy, of household energy demand Australia's energy demand is attributed to households. 13% of Australia's water demand is also attributed to households. And the second largest use of energy within our households is hot water heating, second only behind heating. Let's just give you a little background and insight into the importance and significance of why we're looking at the particular systems as part of this particular research. And that is solar hot water heaters and rainwater tanks. These became mandatory for all new buildings in Victoria from 2005 as part of a Victorian-only variation to the National Construction Code in Australia. And so there are particular requirements around this that are outlined in the National Construction Code, Volume 2. This applies just to, and those of you that aren't familiar, maybe people online aren't familiar with the Australian National Construction Code. Class 1 buildings are detached housing and horizontally attached housing, so residential housing. And those requirements are around in terms of solar hot water, if you had gas connected, they must be gas boosted solar hot water. If you didn't have gas, they had to be heat pump, but not boosted with grid electricity, for example. The rainwater tanks, a minimum of 50 metres squared of roof area feeding into them, a minimum of 2,000 litres. So the specific requirements set out in the National Construction Code around the installation of these systems, and it's one or the other, although some houses have obviously chosen to use both. Previous studies that focus on the uptake of these systems have tended to look at the benefits, or the barriers, I should say, and the motivations of why people have chosen solar hot water heaters or rainwater tanks over one or the other. Very few, in fact, I didn't find any studies that have actually looked at correlating the uptake of either system against particular household characteristics, which is what this study actually does. So the aim of this study is to analyse the historical trends in the adoption of solar water heaters and rainwater tanks in Victoria, and in doing that to look at correlations between the uptake and specific housing characteristics. And in this case, we looked at geographic distribution, some socioeconomic indices, project cost, and allotment area. And I'll get into the actual data that we looked at in a second. So the database which I referred to earlier was obtained from the Victorian Building Authority. So it is a database of all building permits issued in the state of Victoria. An electronic version of that exists from 1997 onwards. There are obviously hard copies that we didn't access from before that date. And a record of the installation of either a rainwater tank or a hot water system is made at the time of applying for a building permit. So that data actually contains that information. That's the intention, anyway, of installing one of these systems in a project at the stage of applying for a building permit. The data that we obtained from the VBA was cleaned. There was about 1.4 million individual records within that database from 1997. That was cleaned, and about 50% of that data was incorrect or was not in the format that we required. So different fields in the wrong field, different information in the wrong field, and so forth. So we went through and cleaned that out so it was consistent throughout every single record. We found there was just over 1 million unique projects within that that database. The extra 400,000 were things like a demolition and then a new build for the same site, for example. Project costs were adjusted. So this database included a whole lot of information around project address, the architect, the builder, the cost of the project, the number of stories, the size of the block, the size of the house, the types of materials used in the buildings, a whole range of different fields and information that were collated as part of the building permit application process. So prices were, so the costs of the projects were adjusted for inflation to December 2021 level, which is when we do the actual analysis. And the information on the use of or selection of a solar water heater or rainwater tank was only available from 2006. So this became mandatory in 2005. Data began to be collected from 2006. So we then narrowed down the data we were analysing from that point onwards until 2019, which is when we had data up until. That left us with about 500,000 records, individual projects. We then excluded non-Class 1 buildings because they are not required to install one of these systems within them. We then geocoded all of these 500,000 projects. So we used a tool from AURIN, which is the Australian Urban Research Infrastructure Network, based at the University of Melbourne, and we used the Australian government's geocoded national address file to locate every single one of these projects on a map of Victoria. And I'll show you that shortly. And as part of this project, in working with NDAP, as I mentioned before, we actually established or developed an online interactive web-based visualization portal where we can actually interrogate all of this data, looking at correlations between any one of the fields within the database. And this is just one example of how we did that. As I said on Wednesday, you'll see another version of that, or another way of interrogating that data. So extremely powerful in terms of the system we set up behind this, and what we can do with it in the future. We then move on to the approach. As I mentioned before, we looked at the geographic distribution of the projects that had either a rainwater tank or solar water heater. We also looked at the project cost and correlated that with whether projects had a solar water heater or rainwater tank, the allotment area, the block area, site area, whatever you want to call it, and also some socioeconomic indices, which I'll talk about later. There were 6 socioeconomic indices we looked at. So moving on to the results then of this analysis. This one, first of all, looks at the number and the proportion of each system from year to year since 2006 when they became mandatory. You can see here that at least 30% of projects did not record whether they included one or the other. Okay, and that's just the nature of the database, is that not every project recorded it as much as they should have. There was a preference for rainwater tanks early on, up until 2007, as you can see there, and then the preference for solar water heaters increased over time up until 2019, as you can see that increasing. One of the main reasons for this was because those of you that are from Australia and particularly the Eastern Seaboard, the Millennium Drought, we were in the middle of that up until about 2010. And so as you can see by that time, it was later in the Millennium Drought, and so the desire, I guess, or the perceived benefits of having a rainwater tank were reducing. And so that's possibly one of the main reasons why rainwater tanks were more popular early on and became less popular later on, because everyone needs a water heater. Not everyone needs a rainwater tank. And so by the end of it, there's a very small proportion of houses that actually had both systems, as you can see in the pink. That actually increased over time. It's increased from 1% to about just over 3.3% in 2019. We look now at the geographic distribution of the houses that have got either a rainwater tank or solar water heater. You can see here it's fairly, there is really no trend in terms of distribution of those systems. What we do, and just to give you an idea, the red is actually preference for solar water heater, the blue is a preference for rainwater tanks. And is that 10 minutes already? Okay, I'll speed through this. So as you can see, the redder it is, the higher the preference for solar water heaters. There is a large preference, as you can see, up in the Mallee region. It's possibly because many properties already had rainwater tanks, because many properties in more regional, remote areas don't have mains water. So that's one potential reason why the preference was for solar water heaters, because they possibly already had those rainwater tanks. We also found that in Metro Melbourne, there was a large preference for rainwater tanks rather than solar water heaters. And that may be because they possibly had gardens that needed watering more so than, or people that wanted to maintain the gardens more so than people in more regional areas. Looking at the correlation to cost, and you can see here that cost, the higher the value of the house, the more likely that someone was installing a rainwater tank over at least over $600,000. That preference was obviously lower for the, also similar for the lower valued houses, higher preference for rainwater tanks there. I'll skip through this. This is all in the paper if you're interested in looking at it in more detail. And then looking at the correlation to area, so this is allotment area or site area. You can see that the preference was mainly for rainwater tank, for solar water heaters with smaller blocks, and that reduced the larger the block got. And obviously, the larger the block, the more space you have to install a rainwater tank. So the reason why preference was not for rainwater tanks for smaller blocks is because they typically don't have the space. And this may have actually increased further since since the millennium drought as well, because our blocks have got smaller and smaller since that point in the last decade or so. The other thing is with the cost, the higher the value of the project, possibly the larger the blocks, and so they had also a preference for rainwater tanks as well. This is really hard to see, apologies for that, but this is looking at the socioeconomic indices. There's 6 indices we looked at. I won't go through them, but basically looking at social advantage, social disadvantage, economic opportunities and things like that. This data comes from the ABS, from the census data. The only very small correlation, but the only correlation we came up with was a preference for rainwater tanks in rural areas and a preference for solar water heaters in more urbanised areas, and that's shown in the data we've got. But the correlation is very limited or very low. So just concluding, there was an initial preference for rainwater tanks early on, possibly because it was aligned with the millennium drought and the tight water restrictions that we had at that time, particularly in Melbourne, but across Victoria. Since 2008, there's been increasing preference for solar water heaters. As I said, this is probably influenced by the millennium drought, but also that preference for solar water heaters is probably influenced heavily by the reducing size of our house blocks, blocks. We need to look maybe for alternative water saving solutions for those places, those houses that don't have room for a rainwater tank. What else can we do to reduce water in those particular situations? Geographic distribution may help inform targeted policy and business opportunities. So if we look at areas where there aren't many solar water heaters installed or there aren't many rainwater tanks installed, maybe that's an opportunity for businesses to go in there and come up with solutions to deal with the water demand or the energy demand for those particular households. And the analysis of correlation with other project characteristics that we've got in the database could be really useful and interesting as well. And I'll just acknowledge the VBA for their assistance in this project. So thank you.
Thank you very much. We're starting to slightly run over time. So if we can have a question, one question maybe, folks. Nothing?
I think in a lot of cases it's about the money. Sorry, a lot of cases it's about the money. So if it's going to save people money, which obviously solar water heaters do in most cases, then yeah. If the waters, if there's not, the rain is coming and there's no need for water to water gardens and so forth, then if they can save money with a solar water heater, then they will. I think the other thing is that as I said before, you need a solar water heater, you need a water heater of some sort. You don't need a rainwater tank, and so I think in many cases, that is what you put in, and that's what builders will typically put into most housing as a.
Another question.
Okay. Yep. It's the rationale by the state government to enable. Read the question. So what is the rationale by the state government to enable either a rainwater tank or solar water heating? I can't speak to the state government, but I think the HIA would probably not like us to be encouraging or wanting everyone to spend more money on putting everything in. I think it's a good call in terms of why should we be saving just water or just energy? I think we should be looking more holistically. So, but I can't answer that in terms of the rationale. Yep.
Cool. Right. Thank you very much. And then our last presenter for the day, thank you all for waiting patiently for this, is Alireza Morshedi, and from my part of the world at the moment, and he's talking about evaluating the impact of building material selection on the life cycle carbon emissions of South African affordable housing, which I think is an excellent question to ask.
Thank you so much. Good afternoon, everybody joining us today, even in person or the virtual. So very shortly, I just introduced myself. I'm Alireza Moghaydi, Senior Research Officer from the University of the Cape Town, South Africa. And I'm presenting on behalf of my colleague, Mark Masron, Karen Lejeune, and Cathy Michel. So I'm just trying to evaluate the impact of the building materials, selecting on the life cycle carbon emission of the South African affordable housing. So the rapid development and the urbanization in the global South cities, especially in the South Africa, pose a high demand for the affordable housing. If I want to give you some sort of like a background, in only South Africa, we have a backlog of around 2 million houses. So you just see the huge demand and the movement of the government to creating a lot of affordable housing. If you look at the building and particularly the housing, as you just see in that one, 35% of the energy is just used by the building and 38% of the emission is just generated by the building and the housing. There is a very limited research done in the South Africa or in the global South regarding of this material we are using for the affordable housing. So without any research, we just try to make some houses and just make a problem for the residents or the government for the next 50 years. So the research question we just try to answer here, what impact do building materials use in the main housing component? And how we can just try to minimize this impact through the constructing of affordable housing. The methodology we use here, we just use the two common affordable housing design in the South Africa. Then we are just select the 5 main building components: building environment, building envelope, internal wall, flooring, windows, and the roof system. Then we just look at the 3 scenarios. We just create the current scenario, which we call it conventional system, which we are just creating that one as a basic and the base study. Then we just go to the alternative, and then we just go to the green. Then we just look at the life cycle emission and also the energy for the construction phase and the operation phase. So we just use the H software, which is just created by the World Bank, and we are just trying to use it as an open source software for housing. And then we are just look at the life cycle energy and the carbon emission of this different scenario and the 2 common buildings. So the case study, if we just look at that one, we just get the case study 1 and case study 2, very similar things, and it's just very typical things you can just see across not only South Africa, whole Africa. The first one is a 42 square meters, 2 bedroom, and the other one is a 60 square meter, 2 bedrooms. And I'm not go to the details of those things because of the time. Then the materials, we are just try to select it as a conventional scenario, alternative scenario, and the green scenario is here. For example, in the building envelope, we just look at the masonry clay bricks, which we are just very common here in Africa and the South Africa. We are using that one. For the alternative, we just look at as a concrete block. And for the green, we just look at the Ramad earth system. As an internal wall, we just look at the half brick wall, plasterboard timber on the stud. And lastly, we just look at the straw blocks. And the similar things, we just look at the different scenario for the conventional, alternative, and the green. Then we just model the 3 scenario for the 2 case study, and this is the result. As you can see here, as you can see, the building envelope is just get the most significant energy, embodied energy, and also generate the most CO2 during the construction. Then followed by the roof system with the purple one in the bottom. These are the main contributors to the CO2 and just get the most energy because of the energy embodied of the materials. The comparison of the 2 case study, as you can just see here, if we are just moving from the conventional to the alternative or to the green, we can just save 55% and the 76% respectively from the energy side, and also from the construction phase, and also for the operation phase is 1.3 and the 0.29%. We can just save that one. As you see here, the most of the saving is just happening during the construction phase because of the absence of the heating and the cooling system for the affordable housing in the Africa. So the majority of the changes is happening during the construction, which we just try to minimize the energy embody and the carbon embody of the material. And the total, if you look at the last row, you can just see how much carbon we can just save by moving from the conventional system to the alternative and the green by only changing some sort of like a material, have a better study before we just try to construct. And overall, in the life cycle, we are just able to reduce the life cycle by the 7.8% and almost 10% for the whole life cycle of the building. As a conclusion, modifying the building materials from the conventional to alternative and the green materials can reduce the 55% and the 75% respectively. And for the life cycle, we can just save more or less around 10% by just only changing the materials. Changing the building materials has a more significant impact on the carbon emission in construction phase than the operation phase because of the lack of the cooling and heating system. So we are just trying to look at these changes, how we can just go to the net zero building. South Africa is already accepted moving to the net zero building by 2030 for the new building and for 2050 for the existing building, and is included the affordable housing or the social housing. We need to just do that one. So this is the initial study. The result of this one, it will be reflected to the next one, which is just a net zero. And finally, changing in the material used for the affordable housing, alter the method of the construction for the purpose of the material, and also lower the life cycle carbon emission produced by the housing, improve the sustainability of housing, and also the quality of life of the residents. Thank you very much.
Quick.
Yeah,
I think that's quite interesting. Any questions from anybody? Yes? So people in Teams can hear you.
Yeah. So if I understood correctly, if the building doesn't have heating and cooling system as such at all, still there were quite substantial emissions from the operation phase. So what were the cause of those emissions then?
So there is two cases here, as you just mentioned. If we have a heating and cooling system, we have a higher percentage of the energy and the carbon. And if we don't have it, that one, in the absence of the water heating and the cooling, we have a less. But still the duration of the operation compared to the construction or the energy and body of the materials is very different. 1 year construction to the 50 years of the lifespan of the building. Still, this material we just try to study is just not a well isolated material. That's why we have some sort of like a leak in the system. The people, they just using their own heating and cooling system, and still it's just getting the energy, but it's just not standardized or not some sort of like a centralized heating and cooling system in this kind of affordable housing, because they're just constructed by subsidy of the government. Sorry.
Thank you, and thank you for your presentation. Just a quick question. Did you consider the end-of-life impacts of the materials at all within the life cycle characteristic, and any differences between different end-of-life outcomes?
Thank you very much. For the initial study, as I just said, this is the first result of initial. No, we didn't do that one. But for the net zero, which is just a project with the national housing of the South Africa, we just try to do that one. So we are just targeting for the net zero. The end life is just included. Also, we just try to move to the net zero. What material specifically, we can just use that one. And also we just try to include the heating and cooling system to just standardize the heating and cooling during the operation.
Maybe you can just read them. The green approach, shifting aside the alternative approach.
Yes. This is, we have a very big, huge study. We call it SEO in the South Africa, or we are just founded by the Royal Engineering. It's just a stand for the Sustainable, Innovative, Affordable Housing. So this one is just one very small aspect of that project. Under the SEO project, we just try to look at the well-being and the quality life of the residents, how we just do that one. That's why we just try to move from the constructing some sort of house which is just not sustainable, and the people, they suffer in the 50 years of the lifespan. As one of the audience, they ask about the absence of the heating and cooling system, because there is no cooling and heating system, and the material we are using is not well isolated. So the people, they just really suffer. During the winter in the South African building, you should agree with me, it's very cold. Sometimes inside the building is colder than the outside. It's very funny. In my office, when so when I'm just feeling cold, I'm just going outside. And during the summer is the same scenario. So inside the house is just hotter than the outside, because we are just using the conventional, mostly more brick and mortar and something like that. So we are only just go to the changing of the material or the design of the house using some sort of like a more passive design, but we're just thinking about the well-being and the quality of life of the residents. What local material we can use to improve the local economic, which material the local residents, they rather to just use that one, what kind of system or technology we can just do that one. Because we just think by improving the sustainability of the building, we can just reduce a lot of operation costs. Then we can just increase a little bit of the construction costs to adjust everything. Another question.
Don't know if there's another question, but it looks a little bit like it's the well-being relations to the kind of construction materials. Now, I know that we've had issues in South Africa with rammed earth or earth bricks in the subsidy housing market. Have you looked at that as well? And whether it's one thing to tell people it will perform better in terms of.
We have one thing in the South Africa is very interesting in the social aspect of that one. That's why we aren't just try to include it, but in the some certain aspect. The people sometimes they just believe the conventional materials. They have a knocking test. So usually they come and just test the house with the knocking. If it's not sounds like a brick or the concrete, they say this is not a house and they are not accepted as a house. So no matter what kind of technology, what kind of the system, what kind of the innovative technology like a modular system, prefabrication, we just try to do that one. If the social or the resident, they are not accept that one, they are not occupy that one, they don't want to use that one. And one of the aspects of well-being is just likely more on the social. So we just try to very carefully look at that one, because in the diversity of the South Africa, we have a lot of different culture, we have a lot of different people. So it's just very carefully, we are just trying to look at that one, but not in this phase, in the second phase of that one, because it's very complex. You should too.
Thank you very much. I think if there's no other questions, we've come to the end of this session. So thanks again to all our presenters. And I hope that you're going to go back now and read the papers and see what this is all about. And I think from here on, it is off to the town hall for drinks, which is well deserved by this point. So thank you, everybody, and see you at the town hall. And thank you for all our online people. At least you can go off and make yourself a cup of coffee. You may not be able to join us here in wonderful sunny Melbourne. But thank you for joining us. And for those of you 3 o'clock in Brazil, I hope you can go to bed now.